Does that work? It's all good? All right, cool. Thanks. Good morning. Thanks for being here. I'm very excited to be in this community. I'm getting to know more new people here. So today I'm going to talk about somewhat a kind of different topic than some of the talk I've seen before. It's on capacity of information processing systems, and I'm from Stanford Graduate School of Business. It's a joint work from Laurent Massoulie in MSR in RIA in France. So before I start, I kind of want to give a little high-level pitch on what are the main ideas of this talk. I guess there are two things that are kind of interesting about this. One is we're looking at a question of system design. So on top of algorithm, the high-level idea here is to think about, under the constrained resources, how to design a system, which means we probably have more freedom than just designing algorithms. And the second question is we're looking at a state of steady state. So we're designing a system that supposedly runs for a long time. So we not only care about, in a sense of finite time performance, but also what happens on average when the system runs for a long time. Okay, so a quick slide about the high-level motivation. We're looking at a system that, roughly speaking, called extracting information as a goal of their operation. So here, for example, we're looking at crowdsourcing, where you have a bunch of images unlabeled, nobody knows anything about them. The decision maker dispatches images to a bunch of people and collects from each person some noisy information about that image. And at the end of the day, the ultimate goal is to kind of pull together this information and label for each image, some kind of underlying truth about that. What kind of animal is in there, or whether it contains certain object. And the same system can be thought of in the context of medical diagnostics. We might be blasting the file of patients to different specialists with the hope of identifying the disease for each patient, or manufacturing testing. So here the items will go through a bunch of machines and try to identify what kind of fault it is and how to do that efficiently. So in all of the examples, essentially the decision maker is trying to aggregate information, even though the information is noisy, and hopefully at the end, as a result of aggregation, we can achieve certain accurate classification. So again, if we look at the three examples, there's this very common thread of constraint going through, because at the end of the day, if we had infinite resources, problem would have been easier. However, in crowdsourcing, we're doing this with a human. So humans probably can label 1,000 images a day or 100 images a day. And in the case of other examples, we might have a machine that's performing this, or the task consumes certain computational resources. So this talk, we're trying to figure out a model or a framework to address how to do efficient information extraction under the constraint of finite resources. Okay, so that's essentially the high-level idea here. Okay, so let's jump into the model. I'm going to build the model from the little black box and start kind of expand. So to start, we're just imagining that the model is a waiting room. A waiting room is just a place where jobs stay and we can do stuff about it. And so in this black box, here we're actually receiving input from the outside, which are jobs arriving to the system as certain unit rate Poisson process. It's not so important about the unit rate, neither about the Poisson. The idea is there's just a steady stream of jobs coming to the system that we need to do something about them. Each job I has this hidden label, HI, representing essentially the core type of the job. So in this case, a job I, the true label says cat. And we'll assume that HI is drawn from some finite set script H. And also that labels, these hidden labels, are generated IID according to some potentially unknown prior distribution. Okay. So the ultimate goal of the system, somehow, is that at the end of the day, we want to produce for each job I an estimate or a guess of the true label, which we call H prime. And we're happy if H prime is equal to the true label, and unhappy otherwise. So if we say cat, we're happy. At the end, the result is dog, then we're unhappy. And the constraint here is that we want, for each true label type little h, the estimation error be no more than delta. Okay. So delta will be our, essentially, accuracy parameter for the rest of the talk. Okay, so how do we get that? How do we get from these jobs to their estimated label? So we'll assume that the system essentially employs a finite group of experts, servers, or people that behave in the following fashion. They're of k types, and when I give a job whose true label, which we don't know, is little h, to an expert of type k, then we'll assume that the result of this interaction would produce a random variable called outcome x, whose distribution is given by this PDF, this distribution, which is P of hk and the outcome little x. The key here is this family distribution essentially just depends on two things: the true label of the job and the true type of the expert. We'll assume that we know, of course, who is who, meaning we know the type of the expert, and we know their fashion, their way of interacting with jobs. So we know the matrix of distributions P, H, K for all pairs H and K. And the idea is essentially using this knowledge, can we kind of go back and back engineer out what type of job it really was inspecting. Okay? And for now, we'll assume that this entire matrix is known by the decision maker, presumably from training, namely by giving people already labeled images and try to estimate how they behave with respect to certain job types. Is that clear? Okay, cool. So a more concrete example. So here I'm giving you an example of this matrix. In this case, the space of all job labels are cats, dogs, and hamsters. And there are three types of experts. And the nature of interaction is that each expert would just say, I like the animal, I don't like the animal. Okay? So A is a Bernoulli random variable with the parameter little a, and let's say B denotes another Bernoulli random variable with a different parameter B, and A is greater than B, so they're different. And this entire matrix interaction is basically given here, ABB, BAB, BBA. And here the column corresponds to jobs, and the column corresponds to experts, and the row corresponds to jobs. So in the first case, let's say type 1 expert essentially kind of likes cats more than dogs and hamsters, and is otherwise indifferent between dogs and hamsters. Okay. So the idea is, if you look at this matrix, it's not that hard to tell that there is some way to distinguish animals. You probably send the image to the first expert. If you see A, well, it is a cat, if you just keep repeatedly doing this. But if you see like the statistics not so different, then you probably route these jobs then to the second expert to distinguish whether it's actually a dog or hamster. And the message is that by pulling together the information from these experts, you can distinguish the job types, even though each expert might not be able to distinguish all of them. But if you just kind of mix and match, and the final information will be strong enough to make that distinction. Okay, so now we know we have these kind of response functions and for the experts' outcomes. How do we actually reach a conclusion for the job label? Well, that's not too hard, especially not for this community. So let's say we've had a history of inspections by routing these jobs to different experts. It looks like this. So for a given job, I might have a sequence of pairs. Says, well, the first inspection was done by expert type K1, and the result was some number X1, and K2, X2, and so on and so forth. So given this history for a particular job, one very reasonable estimator you will use is this sort of maximum likelihood estimator, simply essentially computing the probability that given this is the expert, these are the experts I route the job to, what are the chances that I solve this particular realization of outcomes. And then I maximize over the potential labels of the job and pick the biggest one as my guess for the job label. Okay, so that's essentially the estimator we'll be using in analyzing our algorithms. Okay, so far we've had the jobs coming in, we have experts providing information. What are the constraints? Well, the constraints that we have finite number of people, and each inspection will take some non-trivial resource out of the expert. So we'll assume that there are essentially a finite m number of experts, and the fraction of expert type k is fixed to be some number rk. And in this work, we'll fix rk and vary m. So rk can be thought of as a parameter, where m is a variable of system size we're going to decide. And each inspection will occupy an expert for a finite amount of time. For now, we'll assume it's just 1 unit of time, but you can make it arbitrary as long as it just depends on k. And we will require that the system be stable, in that we need enough people so that eventually all jobs get processed in finite time and the whole backlog doesn't just explode to infinity. That's the stability condition here. Okay, so now the picture is complete. We have a black box of waiting room. Jobs come to this waiting room with some random hidden label. And while in the waiting room, we send jobs to these experts, and we send to them. We get a label, an outcome slapped on to each inspection. We put it back to the waiting room, and we repeat these things as many times as we want, with the constraint that the experts can only be working on one job at a time, and it will take like 1 unit of time to work on a job. And at some point, we feel, okay, we've had enough information about this job. We let the job leave the system and put an estimate on it. Okay? And we see the policy is essentially accurate if the error from this procedure is no more than delta. And that's it. That's the system. Is that clear? Okay, good. Okay, so now let's talk about how to measure the efficiency, how to do stuff in the system. Just for formality, we'll call inspection policy fee as this procedure that decides in real time, first, how to assign inspections to jobs, who to look at the job next. This potentially is based on the entire past history of the system, and when a job is eligible for departing from the system, given the information we've collected so far. Basically, this is like a machine and algorithm that just kind of look at the state and decides what to do next. So let's talk about how to then evaluate these inspection policies. So we define a quantity m of phi, pi delta, as the smallest number of experts needed for stability under the following thing. Assuming I'm using some policy phi, the job type distribution is pi, and my required estimation error is delta. Now, if you look at this expression, essentially it says, well, if my delta is very small, I want the job to be labeled very accurately, then I probably need a lot of people, because each job will require many, many more inspections to just really make sure the type is right. Okay? So then we can define another quantity, m star, as essentially the optimal policy, given the input parameter pi and accuracy parameter delta. So I'm going to min over the universe of all causal policies as basically a performance benchmark. Okay, now we can kind of compare them. So for a given policy phi, we call the policy resource efficient. If for all input distribution pi, the ratio between the number of people I need under phi and the number of people some theoretically optimal algorithm needs converges to 1. So asymptotically, I need minimal system resource to do the job. Okay, and a stronger notion is called strongly resource efficient if such dependency does not even depend on what kind of an input mixture I'm getting. Okay, so the main result, we essentially show the following. So fix any output distribution, outcome distribution, P, and any expert mixture, R. Then there exists a strongly resource efficient policy. And in particular, there's some policy that we can plug in such that when I take the soup over all input distributions in the regime of delta grows big, then the ratio between the number of people I need and the optimal system size is upper bound by 1 plus essentially little over 1. And the particular scaling is square root log 1 over delta over log 1 over delta. And the feature, another important feature is that the policy is so-called prior oblivious, meaning that we just put that thing in and we don't really need to give the policy the particular pi that dictates the mixture of jobs, which we actually don't know. Okay, so a few comments. This theorem makes essentially no restriction on the outcome distribution other than some kind of necessary conditions to avoid triviality and the fact that it's finite support. In practice, as I said, pi is very hard to know because we don't even know the job labels to begin with. And so it's nice to have a bound that holds uniformly over all pi and that the inspection policy is pi oblivious. And we have some sense of how optimal this scaling is, and I'll be happy to talk offline. So quick run through the related work. In fact, the work is very much inspired by the classic work on the, I guess, classic and modern work on sequential hypothesis testing, where we're choosing different experiments each round to distinguish certain hypotheses. And the main difference there is that typically cost is measured by sample complexity, whereas in our case, we're thinking about this kind of more multidimensional characterization of resource constraints. We also kind of get inspirations from the work in Kuang networks, because as you will see, hopefully, given time, the algorithm kind of treats the certain notion of aggregate system workload, a system-wide log-likelihood ratio as a certain notion of workload, and use certain Kuang theoretic algorithms to prove stability. Okay, so how much time? I got probably 3 minutes. All right, I would just probably skip the details of the algorithm, and suffice it to say that the core of the work is to essentially couple the behavior, both of the system lower bound and the algorithm that we use, to a certain linear program. So the linear program essentially says, if I knew the type of each job, and my job is really not to learn what their types are, but to ensure I can convince someone else that I got the right type, then we need to devote a certain amount of inspections for each job, such that the amount of KL divergence accumulate of the true label against a false label is sufficient. And essentially, this LP characterized the amount of work needed to be done in that system. And we show that our algorithm actually converges essentially to the minimal solution of the LP, and also any other algorithm must be at least as big as the optimal solution as well. Okay, and the algorithm itself kind of utilizes a three-stage structure. The first stage, we create a course label of all the jobs by using randomized inspections from experts. In the second stage, we use these course labels to essentially bootstrap an adaptive policy that aims to minimize a quadratic potential function of the aggregate system workload. And hopefully everything can be done in that stage. But if things go wrong, we route the jobs back to a third stage to kind of relearn their label, and finally everybody departs from the system. And at a very high level, essentially a dichotomy, it's a dichotomy of generalist versus specialist. We route jobs first to generalist, and then be looked at specialist. And if things don't work out, we route them back to the generalist again until everything is labeled correctly. On the technical side, because the system is a very high-dimensional Markov process, because the number of experts actually grow to infinity in this regime, we use a so-called stochastic fluid model to capture the dynamics of these jobs and their information in the system, and we prove that the pre-limit system converges to a fluid limit, and that there is a certain very strong contraction property of the fluid limit with respect to quadratically optimal function, and hence this implies a stability of the original pre-limit system that we aim to analyze. Okay, so the point of this work is to propose, hopefully, a new model, an architecture, to achieve provably resource-efficient information processing. And the proof relies on the analysis of a stochastic fluid model of a certain notion of aggregate system-wide workload. And the open question is how to do this for simpler heuristics. We have some guess, but the analysis is not quite there yet. And the dependencies on the type of outcome distribution is quite weak at the moment, which we hope to strengthen. Our question seems to also point to some interesting problems lying at the intersection of these adaptive control, stochastic analysis, and also statistics and information theory. So hopefully we'll get to explore that in the future. Thank you very much.